All right, today we are going to be talking about inverse and joint variation. And this is actually kind of tied to direct variation. You learned it in Algebra 1. It says here in Chapter 2. I'm not sure if we've already talked about that or not. But anyways, direct variation looked like this when you guys were in Algebra 1. It was some type of y equals mx plus b relation where you only have something in front of x, so you can put a out there. We're going to use a quite a bit today, but you could also put m. The graph looked like it went through the origin, and then we also said that this was a proportional relationship. Today we're going to focus on the inverse variation. It's very similar, except we're going to say that it is y equals a divided by x. So direct variation is a times x. Inverse variation is a divided by x. And here's how it reads. This is y varies inversely with x, and that's the way it looks right there. A is going to be our constant of variation. Usually this is some type of number that we're going to have. Sometimes we're going to have to solve for this number. To solve for this number, if we were to theoretically get a by itself here in this equation right here, I guess we could go put y over 1, and then we could say a is equal to x times y. So, yeah, just like that right there, x times y. So a, or the constant of variation, is always going to be the x and the y values multiplied together. Okay. So the first couple of examples, we're just going to learn to identify the different types of variations that we're going to have here. So usually you want to solve for y on these equations. So if we have this equation, y'all might have had something like this in Algebra 1. You need to get y by itself. We're going to do that by dividing both sides by x here. So then that's y is equal to 7 divided by x. You have some type of constant number up there in the numerator, and then you have x in the denominator. When this happens, we call this inverse variation. Now this one here is pretty close to direct variation right here. It's like having a 1x out there in front, but since you got this plus 3, typically we don't have any constants with these right here. So rewritten equation, this is already solved for y, I guess. But this is none of the variations. And then if you want to put yourself, a reason here, I would say because there's a constant term, I guess. So these will look very basic here with inverse and direct variation. This next one here, if we want to get y by itself, we can multiply both sides by 4. It's going to cancel out, so this is going to be y equals 4x right there. So this one is in direct variation form. Direct. So those are some side-by-side comparisons there. Okay. The next thing here, we're going to go and find the constant of variation with these inverse variation relationships right here. So we know that these should look like this. Y equals a divided by x right there. So we're going to solve for our a value. So the way I usually do these here is label these as x and y, and then I'm going to plug it into y equals ax. Okay, and you can write out that first step there if you don't want to. You don't need to, but you can go 3 equals a divided by, I guess, 6 right here. Then you're going to get a by itself. You're going to do that by multiplying both sides by 6, and that's going to get us 18. Okay, so this is our constant of variation. And I guess I said the word constant earlier here, but I was referring to a constant term versus a constant of variation. The constant of variation is the a value in this case. And they didn't ask us to write the full equation out, but this is the equation right here. Okay, so doing a little bit more than needed there, but that's all you got to do. So essentially, really, you just got to multiply your x and y values, and that's going to be pretty consistent across the board. So with this one here, I guess we'll go 12, and then equals a divided by 4. So I guess we'll multiply both sides by 4 here. We're going to get that a is 48 right there. And then if you want to put that together in your equation, you'll have y equals 48 over x. So pretty straightforward right there. Just need to know what your equation looks like right there. Okay. Here's how a typical problem looks like with these inverse variation problems here. So you have the variables x and y vary inversely, and when y is 7, x is 4, write an equation that relates to x and y, and then find y when x is equal to 2, or negative 2. So be careful on these. A lot of people see this, and they want to set up a proportion. Don't do that. Okay, proportions actually are, in a way, it's a direct variation relationship. Inverse variation has a totally different relationship here. So these, you do not want to set up a proportion. You will not get the right answer. So be really careful here on these. So the typical way I solve these problems here is kind of I do 3 steps here. What we're going to do is find the constant of variation. I'm just going to abbreviate that. Then we're going to make an equation. Okay, and then after that, we're going to solve for missing variable. Sometimes they ask us to answer a follow-up question. So kind of 3 things here. So first thing, plug into y equals a over x. And we're going to take those y and x values that they initially got us here. So apparently you got a relation, and then when y is 7, x is 4. So I'm going to plug 7 in for the left side, and then 4 on the right side in the denominator. We're going to multiply both sides by 4. We get 7 times 4, that's going to be 28. There's your a, there's your constant of variation. Done with that step. Next, make an equation by essentially plugging this right back in. Okay, so y equals 28 over x. And that models whatever this situation is. They didn't really give us any context, so we don't know, what x and y represent. Here in a moment, though, we'll look at a few word problems that show inverse variation in the real world. So there we go. Make an equation, and then the next thing here we're going to do is solve for y when x is negative 2, which all you need to do is literally plug in negative 2 in for the x and for that equation, and then simplify for that y value. So apparently that'll be negative 14 right there. Once again, we don't know what the context of the situation is, but that's how that works out there. So okay, so that wasn't too bad there. So let's do this next one here. Same idea. Got 3 parts. First of all, find the a value when y is 15 and x is 1/3. Notice here, keyword varies inversely, x and y. So this will be y equals a over x. Okay, and then we're going to go plug in those values that we have. Y is 15. Okay, this is kind of weird. Apparently the x is a 1/3 divided by a fraction. We'll handle that here in a second. So I guess, a couple ways you can do this here. You can change this up here if that helps you out. But really, I would probably just multiply both sides by whatever you're dividing. Right, so we're going to multiply both sides by 1/3. Right, so the 1/3 will cancel out. You get a over here on the right side. 1/3 of 15 is going to be 5. So 5 equals a. That is your constant of variation. Now we're going to go take that and we're going to plug it in for a. So 5 over x. There's your equation. And then the next thing is to find y when x is negative 10. So plug in negative 10. And that gets us, I guess, negative 2 here. And then that's it. Or no, not negative 2. Let's try that again. Let's try negative 1/2. Late at night. All right, so that's that right there. Pretty easy. There's your equation. Yep, so there you go. Okay, next one. This one's a little different here. Each pair of values is from an inverse variation equation. Find the missing value. So what I would do, this is essentially the same exact thing as the last question. So we don't know what's going on when you got 4 comma y. So forget about that almost just for a second here. And let's do the same thing like we did earlier. Let's use this first point. If the x is 2, the y is 5. Let's plug that in. right away. So let's go 5 and then equals a divided by 2. Okay, and then multiply both sides. A apparently is 10. There's your constant of variation. Next thing, make your equation, just like we did before. So that would be 10 over a. Okay, and then last thing here is now we'll go back and revisit this point here. Let's go figure out, let's see, let's make that 10 over x there. All right, and then next thing here, let's go plug in 4 for your x value there. That'll be y equals 10 divided by 4 right there. And then we're going to find the y value for that. And I guess this one here, if you want to get a decimal, you can. I'll probably just reduce it here. I'll just call that 5 over 2 right there. Divide the top and bottom by 2. And yeah, I would just leave it like that right there. So, came out as a fraction. That's fine there in this case. So, there you go. Let's see what's going on with this one. Same idea here. Got your 3 different parts. First thing, find your constant of variation, a over x. So yeah, let's go 6, and it equals a divided by 4. So multiply both sides by 4. That's a is 24. Let's write your equation. Y equals 24 over x. Try not to mess it up this time. And then, yeah, here you go. So we're trying to figure out what's going on when the y value is 3. So I guess we're going to go plug that into the other side. So we have 24 over x. And some of you guys might be able to use logic there. But honestly, if you got x in the denominator, let's go ahead and put that over 1. And then let's cross multiply. Let's go 24 and then equals 3x. And then divide. This will be x equals, I guess, 8 right there. So apparently 8 comma 3. So there you go. Those are those types of examples here. Sometimes you're going to have to determine if something is an inverse variation or direct variation relationship based off of a table. And typically with these here, you want to go and look and see if the products and the quotients of the two numbers are the same. Let's real quickly revisit back up here at the top. We said with inverse variation, the constant of variation is always going to be the x times the y value. So if something has an inverse variation relationship, this product should be the same every single time. Okay, and then what we're going to go and do is we're going to go test and see if these products are the same. Is 5 times 10 the same thing as 10 times 20 or 15 times 30 or 20 times 40? Okay, and then if not, then we're going to go see maybe if it's a direct variation type of relationship. So if you were to get your a by itself here, you would actually divide both sides by x. And that means every single time y over x is going to be your constant of variation for direct variation. So this quotient should be the same. The y over the x should be the same thing every single time if it's a direct variation relationship. So I think on this example here, they're going to give us one example where it's direct variation and then one that's inverse variation. So remember, direct variation, you need the same y over x, and then for inverse variation, you need the same y times x right there. And then if none of those are true, then it's none of the above. So for this one here, we're going to check, and I'm going to check and see if the quotients are the same first for direct variation. So I'm going to see the y value, 10 over 5 right there. We're going to ask ourselves, is that the same thing as 20 over 10, or 30 over 15, or 40 over 20? And these are all the same right here, right? So you can put a check mark next to all of those there. These all reduce to 2 right here. That means your a value in this case is 2. This is a direct variation. Oops. Relation here. Okay. If you get that consistent ratio between x and y. So if you go and check if the products are the same, obviously 5 times 10, that's definitely not the same thing as as 20 times 10 right there. That's going to be 50 here and then 100 right there. Obviously not the same right there. So the products are not the same, but the quotients are. That's direct variation. Okay. Same idea here on this one. Let's see if the quotients are the same. 12 over 1. Definitely not the same thing as 4 over 3. You can pretty clearly see that right away, which is also definitely not the same thing as 3 over 4. Remember, I'm doing y over x values. And then definitely not the same thing as 2 over 6. And you honestly don't need to write it all the way out there. You really just need to show that one of them doesn't work, and then you're good to go. All right, here, let's do this here. So show that 2 sets don't work right there. So then let's go check the products. Let's see, 12 times 1, that gives us 12. 3 times 4, that gives us 12. 4 times 3, that gives us 12. 6 times 2, that gives us 12. That means this is an inverse relation. All right, and then our A values, the product of these, it's consistently 12 right here. And that was a little bit more than they're asking there. Really, we just needed to see if it was an inverse relationship. Okay, so there you go. Let's look at some real world examples. Maybe it's not intuitive right off the bat, like what a real inverse variation relationship here is here. So here's a good example here. So the number of songs that can be stored on an MP3 player varies inversely with the average size of a song. So this one's, slightly outdated here. I don't know if anyone uses iPods or anything like that, MP3 players or whatever. Now y'all just have it on your phones. But sometimes you only got so much storage here. And the whole idea is the bigger the songs are, the less songs that you can fit. So notice here, I'm gonna label the variables this way here. So it's the number of songs right there. So I guess I'll put S for songs, the number of songs, and then can be stored. It varies inversely with the average size of a song right there. So you have the number of songs is one variable. The size of the song will be another variable. Obviously, I don't want to use S twice, so I'm going to put M because I think they're going to give me megabytes here in a second. So we'll just do M for that. So it's going to look like this here. It's usually whatever the first thing that comes, it says the number of songs, and then varies inversely. So that means S is going to be by itself, inversely with the average size. That means the average size of the song is what goes in the denominator. Okay, and then we need some type of constant up in the numerator right there. So this will be S equals A divided by N. A, we're going to solve for. That's going to be some type of number. Okay, so to go and figure out that A value, look at this. A certain MP3 player holds 2,500 songs when the songs are an average size of 4 megabytes right there. So we can do 2,500 for the number of songs, and then A, we don't know what that is, and then we're going to divide by 4. Okay, get A by itself, multiply both sides by 4, that's going to be 10,000. Right there. And that is that constant of variation right there for that specific MP3 player. Okay, so then with that here, we can create a model. We're going to say Y equals, and I guess we're going to use that 10,000 that we just got right there. So I guess that's I'm not sure exactly what that is, I guess, in this situation here. Maybe it's the total megabytes, I guess. But anyways, if you know it's going to be the total megabytes, actually, in this case. All right, and then, so then we're going to take different, I guess, song sizes here. You got 2 megabytes, 2.5, 3, and then 5 here. And then we're going to make a table for this situation here, using all of that stuff here. And actually, I put Y here. Let's go ahead and put the variables we started with here. Let's use S and M. That would probably be the best habit right there. Then I guess we're going to make a table. So just go off to the side here, put S here, or actually, no, let's put M on the left. M is the input. I'm going to input in for M, and then we're going to get different S values. So apparently we got 2, 2.5, 3, and 5. All right. Then just go ahead and plug them into that equation. So if I plug in, I guess, 10,000. And then divided by 2 for the first one there. I think that gets us 5,000. So that means we'd have 5,000 songs if they have that size of 2 megabytes. Okay, 2.5. Not sure what that one would be. Maybe it's 10,000 divided by 2.5. That comes out to 4,000 actually for that one there. So I'm getting that from 10,000 divided by 2.5. Okay. Next one, I don't know if this is going to come out very clean, so we might have to do a little bit of rounding. So 10,000 divided by 3 megabyte songs, it's going to be 3,333. I guess 0.3, honestly, you can't have 0.3 of a song, so let's round down, I guess, in this case. And then obviously, yeah, you got 5 here. 5 goes in the 10,000. 2,000 times there. So that gets you 2,000 songs there in that situation. So yeah, there's you a real-world situation with inverse variation. It's not a proportional relationship. You can't just set up a proportion like normal. You got to use the m, I guess, in the denominator. So I guess a follow-up question here: what happens to the number of songs as the average song size increases? Well, if the size increases, the number of songs, I guess, goes down or decreases or whatever you want to put there. So there you go. All right, let's look here at this next one here. Kind of the same idea. The driving time between 2 specific locations varies inversely with the average driving speed. And then they say the driving distance between Chicago and Minneapolis is actually 400 miles here. So look here, you got driving time. I'm going to go ahead and use a T for that. Varies inversely with the average speed. And I guess I'll use S for that. So I'm going to go ahead and write this model. I'm going to do T equals and then some constant over S. And actually with this situation here, this constant is actually your distance that you're going to be driving. And then, based off of the speed, if we're going faster, then the time is going to the time is going to decrease. Yeah, if the speed is quicker, the time will decrease that it takes, and then vice versa here. So yeah, 400 right here. This is actually our A value. They gave our A value to us. A is 400. So we're going to do T equals 400 and then divided by S right there. So what would be the driving time for an average speed of 60 miles an hour? I'm just going to go and plug in 60 miles an hour into the speed, and then we're going to figure out how much time it takes right there. So let's see here. That comes out 400 divided by 60. Just use my calculator here. It's going to be 6 and then 0.67. Which is basically 6 2/3. I guess in this case this would be hours right here. If we're going miles per hour right here. And honestly, if you think about that, 2/3 of an hour, this is 6 hours, and then 2/3 of an hour is 40 minutes actually. So if you wanted to get a little bit more specific here, we're using our units here. Right there, you can do that there. 6 hours and 40 minutes. Cool. One more here. Because the table below compares the area of a computer chip with the number of chips that can be obtained from a silicon wafer. Okay, I'm not really sure what that means there, but apparently it is an inverse relationship here. So this one, they gave us a table here. So remember, to find an inverse relationship here, we need to check and see if all the products are the same. So we're going to go and check. Remember, A is equal to Y times X. And then we're going to go and see if these are all the same here. 58, I guess, times 448. And that comes out to, let me write it down, 58 times 448. Comes out to 25,984. Okay, and then I'm just going to go and check and make sure some of these other ones come out to that same A value right here. This A value here, we need to do 62 times 424. As long as a few of these are the same, we can probably go and assume the rest are going to be the same. Times 424, and that comes out to 26,288. right there. So actually it's close, but it's not exactly the same here. Interesting. 66 times 392, about 25,872 right there for that. And I guess we have 70 times 376. This one comes out to 26,320. So what model gives this function, it gives C as a function of A right here? So I guess this is a situation where it's not going to be the same exact thing every single time. Not a consistent A value, but it's pretty dang close here. Notice here, this is really close to 2600. This is close to 2600. This rounds up to 2600, or actually 26,000, I should say. So we're going to use and say that the A here is about 26,000. You know, sometimes in life things don't work out perfect where it's the same exact number every time. Maybe there's some type of error or malfunction or something along the lines of that. So yeah, let's go ahead and assume 26,000 here since this isn't consistent here. And then C as a function of A, that means C needs to be by itself here. So we'll go C, our A value is 26,000. And then we're going to put it all over, I guess, the A right here. Okay, and then predict the number of chips when the A, or the area, is 81. And based off of our table, we kind of saw that, you know, this wasn't a perfect table here. And that's how life is, honestly, a lot of the times here. So let's do that here. So I guess we got 26,000 and then divided by 81, and that got me 320 chips. And then I guess, you know, if you can round up, it's 320.1 or 320.9, so I guess we can round up to 321 right there. And then it's chips. And there you go, right there. So that's a real world example where it's not perfectly the same A value every time, but it's pretty dang close. So we're gonna roll with that inverse variation relationship right there. Okay. All right, let's look here at joint variation. So this is actually the combination of the two here. The last type of variation is joint variation. Joint variation occurs when a quantity varies directly with the product of two or more quantities. Here's a couple of examples below right here. So you got Z varies jointly with X and Y. So you have X and Y multiplied. You have some constants, so then Z is by itself right there. Okay, sometimes you might get one like this. P varies jointly with Q, R, and S. So Q, R, and S right there, all multiplied. Here's your constant A, and then that's equal to P. So these can all look a little bit different. Sometimes they'll throw in words like with the square of something or the square root of something. Maybe jointly with this, inversely with that. They get a little exciting sometimes here. So they're all a little different here. Look here, we got Z varies jointly. That means Z is by itself. Usually there's some type of A value. I'll put that out in front. And then apparently we have X and Y. So there's your equation right there. All right, we got to go get A now. Let's go plug in what they gave us. So with the relationship, oh, whoops. Really good. Okay. With that relationship, let's go plug in the negative 75. The X is, I guess, 3. And then Y is negative 5. Okay, and then I guess we're going to go and solve for A. Looking here, I got negative 15A over there, and then negative 75. And then I think that goes in, maybe, is that 5 times? I think A is 5 here in this case. So there's your there's your constant of variation. Same kind of setup here. We solve for A, now we get our equation. So go take Z equals 5 and then XY right there. So plug in your constant of variation. And then go find Z when X is 2 and Y is 6. So we'll go 5 times 2 times 6. 5 times 2 is 10. 10 times 6 is 60. There you go. That's how you do that right there. Sometimes you might have real world situations where you got a couple of different factors and maybe they're all being multiplied like this right here. So let's compare the different types of variation. Write an equation with a given relationship. So I think we're just coming up with generic ones. So you got R varies inversely with S, so that means R is by itself. You got A, and then inversely means that needs to be divided by S right there. You got Z varies jointly with X, Y, and R. So let's put Z by itself. Z varies, that's by itself. Then A, and then X, Y, and R. So just do X times Y times R. Y varies directly with the square of X. So I think that's A, and then do X squared. There's your relationship for that. Apparently this one has stars next to it. I don't know why. Maybe it's a special one here. Maybe it shows up again somewhere. I'm not sure. M varies. So M's by itself directly with the square of N. So I guess we have AN squared, and inversely with P, which means that's got to go in the denominator. So we put this P value, whatever it is, in the denominator. And then there's all your different types of inverse and direct variation and joint variation. And that is it.